So we will continue with the boundary condition. Next we will see conductor dielectric boundary. Here we assume conductor to be a perfect one, that is conductivity tends to infinity, and we know that inside the conductor electric field is 0. I already told you that in the case of a conductor, always the electric charge tends to move towards the surface of the conductor, and all the charge resides over the surface. Actually, this behavior is possessed by the charge in order to maintain equilibrium. So we can say that inside the conductor electric field is 0, and on the surface of the conductor electric field is not equal to 0. Okay. Point to be made clear is inside the conductor electric field is 0 because the charge carriers shows a tendency to move towards the surface and get resided over the surface. So I repeat, electric field intensity is equal to 0 inside the conductor, and it is not equal to 0 on the surface of the conductor. Okay. Now again, this is a two different medium, and this blue one shows a boundary of a dielectric conductor medium, and this first one is a dielectric medium and second one is a conductor. So epsilon is the permittivity of dielectric medium, and here the electric field E is equal to 0 for the conductor. Again we start from the Maxwell's equation. For that we make use of a closed surface A, B, C, D. Okay. And the Maxwell's integral form is integral of E dot dl equal to 0 over the closed surface A, B, C, D. Okay. Now start moving from A to B. What is the total electric field? This AB is lying in the second medium, and the second medium is our conductor, and the electric field is 0 there. So there will be no electric field across AB. Okay. Now moving towards BC. BC is a perpendicular line, and half portion of BC lies in the second medium and remaining half in the first medium. So this lower half of BC will not have any electric field since it is lying in a conductor. But the upper half will be having electric field since it is lying in a dielectric medium, and that component will be En1. That is a perpendicular component across the first medium, En1 into del H2. Then moving across CD. Here this CD will have a tangential electric component because it is lying where in the first medium, which is an electric field. Now I am taking the tangential component of CD as ET. Then I can write the total electric field across CD is equal to ET into del W. And the sign will be minus because AB and BC are in, AB and CD are in opposite direction. Now coming to DA. DA is a perpendicular line. Half section of that lies in the first medium and the remaining half in the second medium. So the upper half will be having a normal component En. En into del H by 2. And it will be having a negative sign because along BC we took the sign as positive, so along AD the sign will be negative. Now coming to the lower half of DA, which lies in the second medium, it will not be having any normal component because the second medium is a conductor, so it will be 0. So in short I can write 0 into del W. This first term is the total electric field across AB, plus 0 into del H2. This term is the lower portion of BC, that is the portion of BC which lies in the second medium, plus En into del H2, that is the portion of BC which lies in the first medium, minus Et into del W, that is the which is CD, which is lying in the first medium. Then minus En into del H by 2, that is the portion of AD which is lying in the first medium. Then minus, this is not plus, minus 0 into del H2, that is the portion of AD which is lying in the second medium. Okay. So finally we will get Et del W is equal to 0, because these terms are 0 and this term will get cancelled. Finally you will get Et del W is equal to 0. From that Et is equal to 0, and we know dt is equal to epsilon Et, therefore dt will also be equal to 0, where dt is a tangential component of electric flux density across your first medium, and Et is a tangential component of electric field across the first medium. Okay. Now next we will go back to the Gauss law, that is closed surface integral of d dot dA is equal to q. I am expanding the dot product, that is d dA cos theta is equal to q. Okay. This diagram and this one both are the same. Okay. So here, in order to find the condition of Dn, I am drawing a Gaussian cylinder. This portion, this much of portion lies in our second medium, which is a conductor, and this much portion lies in the first medium. Okay. So here, since this much portion lies in the second medium, there will be no electric field. Okay. So coming back to this expression, closed integral of d dA cos theta is equal to qa. So here we will not be having any electric field or electric flux density in our second medium. So in the first medium, it will be the cylinder will be having electric field lines, hence Dn will be perpendicular to the surface, and if we are choosing a small area dA, it will also be perpendicular to the surface. Here there is no need to mark Dn and dA because we don't have any electric field in this area. So I can write the total electric flux density in the first medium is Dn, and theta value is 0 because dA and Dn both are in the same direction perpendicular to the surface, so it will become 1, and finally I can write Dn dA is equal to q. From that Dn is equal to q by dA, that is equal to rho s, where rho s is the charge per area, or otherwise known as surface charge density. So this is a condition for a normal component of electric flux density across a dielectric conductor medium. And we know what is the relation between Dn and En. We know Dn is equal to epsilon n. So we can write Dn is equal to epsilon E n, okay, epsilon E n, which will be equal to rho s. Okay, that implies, what is epsilon n? Epsilon n will be, what is En? En is equal to rho s by epsilon. Okay. From that we can find out En is equal to rho s by epsilon. So that is the expression for En across the boundary of dielectric conductor. So here are a few important points that you have to memorize. That is, no electric field is inside a conductor. Therefore, E is equal to 0. Since there is no electric field, rho V will also be equal to 0. Since there is no field, there will be no volume. So, volume charge density is equal to 0, right? And we know E is equal to minus del V, and that is equal to 0 because we have already learned that the electric field inside a conductor is 0. So if you consider these two conditions, that is minus del V equal to 0, then that means V will be a constant, isn't it? If V is constant, then del V will be 0. So we studied earlier that if V is constant over a surface, then that particular surface is known as equipotential surface. Okay. So this particular surface, that is across a boundary of dielectric conductor medium, is equipotential. And that's all in this section. Next we will see conductor free space boundary. Here free space, this is a boundary, and this first medium is free space and second medium is conductor. Conductor, the electric field is equal to 0, free space epsilon is equal to epsilon 0 epsilon r. Now this is a special case of conductor dielectric boundary. For free space, epsilon r will be equal to 1. In the case of dielectric, this epsilon r will be a particular value. It depends upon the material we are using. If it is free space, epsilon r is equal to 1. Now we know Et is equal to 0 for a conductor dielectric medium. Okay. Then similarly we know what is dt. dt is equal to epsilon Et. Epsilon is equal to epsilon 0 epsilon r into Et, and we know for a free space epsilon r is equal to 1. So we will get dt is equal to epsilon 0 Et. Since Et is equal to 0, what happens to dt? dt will also be equal to 0 in this condition. Similarly, we got dn equal to rho s for conductor dielectric boundary, and we have the relation d and e as epsilon 0 epsilon r en, that is equal to rho s. The value of epsilon r for free space is 1, so I can substitute 1 here. Finally, I can write epsilon 0 en is equal to rho s. So from that, what is En? En is equal to rho s by epsilon. So that is a condition of dn across the free space conductor boundary. That's all under this particular section. And boundary condition of magnetic field, that you can do as self-study. Thank you.